The moon's molten churning core likely once generated a dynamo, and the moon had a very strong magnetic field. The timing of the lunar dynamo's demise has been pinned down by scientists now. This is by Jennifer Chu, Massachusetts Institute of Technology. When the Apollo astronauts returned to Earth, they brought with them some souvenirs: rocks, pebbles, and dust from the moon's surface, soil samples, that is. These lunar samples have since been analyzed for clues to the moon's past. One outstanding question has been whether the moon was once a complex, layered, and differentiated body like the Earth is today, or an unheeded relic of the early solar system like most asteroids. Ben Weiss, professor of planetary sciences at MIT's Department of Earth, Atmospheric and Planetary Sciences, and members of his laboratory have found remnants of magnetization in some lunar rocks, suggesting that the moon once emitted a substantial magnetic field, much like the Earth does today. The discovery has opened a new set of questions. How long did this magnetic field last? How strong was its pull, and what sparked and sustained it? Weiss and former MIT student Sonia Tiku have written a review published in Science in which they explored the possibility of a lunar dynamo, a molten churning core at the center of the moon that may have powered an intense magnetic field for at least 1 billion years. Weiss spoke with MIT News about the moon's hidden mystery. Question: how would a lunar dynamo have worked? What might have been going on in the moon and in the solar system to sustain this dynamo for 1 billion years? Answer: planetary dynamos are generated by the process of induction, in which the energy of turbulent conducting fluids is transformed into a magnetic field. Magnetic fields are one of the very few outward manifestations of the extremely energetic fluid motions that can occur in advecting planetary cores. The motion of Earth's liquid core is powered by the cooling of the planet, which stirs up buoyant fluid from the surrounding liquid, similar to what happens in a lava lamp. We have recently argued from magnetic studies of Apollo samples that the moon also generated a dynamo in its molten metal core. Our data suggests that despite the moon's tiny size, only 1% of the Earth's mass, its dynamo was surprisingly intense, stronger than Earth's magnetic field today, and finally support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. The dynamo was surprisingly more intense and stronger than Earth's magnetic field today, and long-lived, persisting from at least 2.4 billion years ago until at least 3.56 billion years ago. This period, which develops and overlaps early epoch of intense solar system-wide meteoroid bombardment and coincides with the oldest known records of life on Earth, comes just before our earliest evidence of the Earth's dynamo. Question: why is it so surprising that a lunar dynamo may have been so intense and long-lived? Answer: both the strong intensity and long duration of lunar fields are surprising because of the moon's small size. Convection, which is thought to power all known dynamos in the solar system today, is predicted to produce surface magnetic fields on the moon at least 10 times weaker than what we observed recorded in ancient lunar rocks. Nevertheless, a convective dynamo powered by crystallization of the inner core could potentially sustain a lunar magnetic field for billions of years. An exotic dynamo mechanism that could explain the moon's strong field intensity is that the core was stirred by motion of the solid overlying mantle, analogous to a blender. The moon's mantle was moving because its spin axis is precessing or wobbling, and such motion was more vigorous billions of years ago when the moon was closer to the Earth. Such mechanical dynamos are not known for any other planetary body, making the moon a fascinating natural physics laboratory. Question: what questions will the next phase of lunar dynamo research seek to address? Answer: we know that the moon's field declined precipitously between 3.56 billion years ago and 3.3 billion years ago, but we still do not know when the dynamo actually ceased. Establishing this will be a key goal of the next phase of lunar magnetic studies. We also do not know the absolute direction of the lunar field, since all of our samples were unoriented rocks from the regolith, the fragmental layer produced by impacts on the lunar surface. If we could find a sample whose original orientation is known, we could determine the absolute direction of the lunar field relative to the planetary surface. This transformative measurement would then allow us to test ideas on the moon's spin pole, wandering in time across planetary surface, possibly due to large impacts. This was from Massachusetts Institute of Technology on phys.org. And then we talk about the scientists pinning down the timing of the lunar dynamo's demise. This is again by Jennifer Chu, Massachusetts Institute of Technology. A conventional compass would be of little use on the moon, which today lacks a global magnetic field, but the moon did produce a magnetic field billions of years ago. It was likely even stronger than the Earth field today. Scientists believe that this lunar field, like Earth's, was generated by a powerful dynamo, the churning of the moon's core, and at some point this dynamo and the magnetic field it generated petered out. And now scientists from MIT and elsewhere have pinned down the timing of the lunar dynamo's end to about 1 billion years ago, and the findings appeared in the journal Science Advances. The new timing rules out some theories for what drove the lunar dynamo in its later stages and favors one particular mechanism, core crystallization. As the moon's inner core, iron core, crystallized, the liquid core's electrically charged fluid was buoyantly stirred, producing the dynamo. The magnetic field is a nebulous thing that pervades space like an invisible force field, says Benjamin Weiss, professor of Earth Atmospheric Planetary Sciences at MIT. He says, we've shown that the dynamo that produced the moon's magnetic field died somewhere between 1.5 and 1 billion years ago and seems to have been powered in an Earth-like way. Weiss's co-authors on the paper are co-lead authors Syed Migani and Huapei Wang, as well as Berlina and Claire Nichols of MIT, along with David Schuster of the University of California at Berkeley. Dueling dynamo's theories. Over the past few years, Weiss's group and others have discovered signs of a strong magnetic field of around 100 microteslas in lunar rocks as old as 4 billion years. For comparison, Earth's magnetic field today is around 50 microteslas. So the lunar magnetic field was twice as strong as Earth's today. Now, in 2017, Weiss's group studied a sample collected from NASA's Apollo project and found traces of a much weaker magnetic field below 10 microteslas in a moon rock they determined to be about 2.5 billion years old. Their thinking at the time was that perhaps two mechanisms for the lunar dynamo were at play. The first could have generated a much stronger, earlier magnetic field about 4 billion years ago, before being replaced by a second, more long-lived mechanism that sustained a much weaker field, though through at least 2.5 billion years. There are several ideas for what mechanisms powered the lunar dynamo, and the question is, how do you figure out which one did it? Weiss says, it turns out all these power sources have different lifetimes. So if you could figure out when the dynamo turned off, then you could distinguish between the mechanisms that have been proposed for the lunar dynamo, and that was the purpose of this new paper, he said. Most of the magnetic studies, lunar samples from Apollo missions, have been from ancient rocks dating to about 3 billion to 4 billion years old. These are rocks that originally spewed out as lava into a very young lunar surface, and as they cooled, their microscopic grains aligned in the direction of the moon's magnetic field. Much of the moon's surface is covered in such rocks, which have remained unchanged since, preserving a record of the ancient magnetic field. However, lunar rocks whose magnetic histories began less than 3 billion years ago have been much harder to find because most lunar volcanism has ceased by that time. And Weiss says the past 3 billion years of lunar history has been a mystery because there's almost no rock record of it. little compasses. Nevertheless, he and his colleagues identified 2 samples of lunar rock collected by astronauts during the Apollo missions that appear to have suffered a massive impact about 1 billion years ago, and as a result we were melted and welded back together in such a way that their ancient magnetic record was all but erased. The team took the samples back to the lab and first analyzed the orientation of each rock's electrons, which Weiss describes as little compasses that either align in the direction of the existing magnetic field or appear in random orientations in the absence of one. For both samples, the team observed the latter, random configurations of electrons, suggesting that the rocks formed in an extremely weak to essentially zero magnetic field of no more than 0.1 microteslas. The team then determined the age of both samples using a radiometric dating technique that Weiss and Schuster were able to adapt for this study. The team put the samples through a battery of tests to see whether they were indeed good magnetic recorders. In other words, once they were reheated by some massive impact, could they still be sensitive enough to record even a weak magnetic field on the moon if it existed? To answer this, the researchers placed both samples in an oven and blasted them with high temperatures to effectively erase their magnetic record, then exposed the rocks to an artificially generated magnetic field in the laboratory as they cooled. The results confirmed that the 2 samples were indeed reliable magnetic recorders and that the field strength they initially measured of 0.1 microteslas accurately represented the maximum possible value of the moon's extreme weak magnetic field 1 billion years ago. Weiss says a field of 0.1 microteslas is so low that it's likely the lunar dynamo ended by this time. The new findings line up with the predicted lifetime of core crystallization, a proposed mechanism for the lunar dynamo that could have generated a weak and long-lived magnetic field in the latter part of the moon's history. Weiss says that prior to core crystallization, a mechanism known as precession may have powered a much stronger, though short-lived dynamo. Precession is a phenomenon by which the solid outer shell of the body, such as the moon, is in close proximity to the much larger bodies, such as the Earth, wobbles in response to the Earth's gravity. This wobbling stirs up the fluid in the core, the way swishing a cup of coffee stirs the liquid inside. Around 4 billion years ago, the infant moon was likely much closer to the Earth than it is today, and much more susceptible to the planet's gravitational effects. As the moon moved slowly away from the Earth, the effect of precession decreased, weakening the dynamo and the magnetic field in turn. Weiss says it's likely that around 2.5 billion years ago, core crystallization became the dominant mechanism by which the lunar dynamo continued, producing a weaker magnetic field that continued to dissipate as the moon's core eventually fully crystallized. The group is looking next to measure the direction of the moon's ancient magnetic field in hopes of gleaning more information about the moon's evolution. So you see, as the moon was closer to our Earth, the dynamo was churning and it had a stronger magnetic field. And now as the moon is moving out, it has a weaker magnetic field. This is by Massachusetts Institute of Technology on phys.org. Please leave your comments and thank you for your support.